Hello, we are covering number and operations, particularly fractions, for the fourth grade this week. Just like with third grade, I wanted to make sure that fractions had their own separate week. Students are uncomfortable with fractions, as I stated before, so the more time that we can spend developing fractions, the better off we are. And here is a list. Look at all of these 7 different particular standards that we need to cover in fourth grade. Again, why it has its own week. There's so many things that we need to talk about. So let's talk about first comparing two fractions using less than, greater than, or equal to. We can compare and order fractions if we have unlike numerators and denominators. So to do so, I'm going to use an area method. Notice that my boxes are the same size, however, one is split into thirds and one is split into eighths. So I'll want to shade 2 copies of 1/3 and 3 copies of 1/8. So 2 copies of 1/3 would be 2 of the 3, and then 3 copies of 1/8 would be 3 of the 8. I can see that 2/3 is more shaded than 3/8, so therefore 2/3 is greater than 3/8. Let's compare 4/5 and 8/10, again using an area model. So on the left, although the unit is the exact same size, they're split into different sizes. So on the left we have fifths, and on the right we have tenths. I need to shade in 4 copies of 1/5 and 8 copies of 1/10, which looks like this. I can see then that the exact same amount is shaded. So therefore 4/5 equals 8/10. We can also use a number line to compare. So on my top line, we already know that 4/5 equals 8/10. So I have a double number line. I split the top line into fifths and the bottom line into tenths. So there are 1/5, 2/5, 3/5, 4/5, 5/5, which we know is the same as 1, and 1/10, 2/10, 3/10, etc., all the way through. I have 4/5 and 8/10 labeled, so I have 4 copies of 1/5 and 8 copies of 1/10 listed here. And I see that they are the exact same location on the number line. So therefore they are equal to each other, just in a different way. Let's order the following fractions from greatest to least using number lines. I've got 3 different number lines. Each number line will represent one of our fractions. I see on the top that I'm split into twelfths. The middle is split into sixths, and the bottom is split into eighths. So when I look at 1/12, 2 copies of 1/12, 3 copies of 1/12, etc., I see where 9/12 is located by counting on my number line. I can do the same with my sixths line. So each one represents 1/6 or 1 copy of 1/6. So I need to go where 2 copies of 1/6 is located, and I see it's listed there. And finally, 4/8. So 1/8, 2 copies of 1/8, 3 copies of 1/8, and 4 copies of 1/8. So when I want to label them from greatest to least, I see that the furthest distance is 9/12. The second one would be 4/8, and the third one would be 2/6. So 9/12 is greater than 4/8, which is greater than 2/6. For your homework, using a number line, pattern blocks, fraction circles, or any other diagram to complete the following listed here. Once you find your answer, and they will be different from a partner's or a neighbor's, so I want you to then answer the questions below, scan and upload your documents back into the Fractions in a Row discussion board. Although you do not have to respond to a classmate's it would be interesting for you to see what they're thinking and their thought processes. So I encourage you to view what your classmates accomplished. When we compare and order fractions, we think about whether the numbers are less than, greater than, or equal to each other. This is true when working with whole numbers and with fractions. Remember that fractions are just a number on the number line and should be treated just as such. We can recognize and generate equivalent fractions, as you probably noticed with that last problem. We didn't have to write 2 6. There was another way we could represent 2 6. So to do so, we'll practice by combining and partitioning fractional pieces on a model and a number line. So what fraction does this model represent? I see that there are 6 pieces, so each piece represents 1/6, and I see that there are 4 copies of 1/6 shaded, so therefore it equals 4/6. Now cut each piece into 3 equal parts. What is the new fraction represented? So I took each sixth and I cut it into thirds. So now I see that there are 6, 12, 18 pieces. Well, of the 18 then, there are 1, 2, 3, 4, 5, 6, 12 copies of 1/18 shaded. What fraction does the point represent on the number line? I see that we are split into 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 pieces. So there are 1/10, 2/10, 3/10, 4/10. Combine every two segments together. What is the new fraction that is represented at this point? So notice when I look at these two here, I combined and reduced them into 1. So I kind of brought it over and dropped it down. So now we're only 1, 2, 3, 4, 5 different segments. So each notch represents 1/5. Therefore, there are 2/5 shaded, or 2/5, whereas the dot is. The number line is certainly underutilized in elementary school, however, is extremely effective for modeling for students. There are many things that we can do with the number line, such as partition and iterating to generate fractions. The roles of number as a multiplier and denominator as a divisor are certainly made clear. The process of fractional parts decreasing in size while the copies of the unit fraction increase in number. There is a clear differentiation between the fraction measure of 2/3, the length of the line segment from 0 to 2/3, and the rational number 2/3 used as a unique point on the line. The ability to partition to represent increasingly more precise measures is boundless. Creating equivalent fractions for any given fraction, be it less than or greater than 1, is easier through the use of the double number line. Not to mention how visual the number lines can be. Have you ever used the multiplication table to create equivalent fractions? So here I have the multiplication tables 1 through 12. Let's say we have 3/5. What else might be equivalent to 3/5? Well, I look on my multiplication table and I see that the row of 3 and the row of 5 are listed. I see also that 6/10, 9/15, 12/20, 15/25, 18/30, etc. are all equivalent to 3/5. How many fractions can we see that are equivalent to 3/5? I can count that there are 12 of them in this table. However, there are limitless. There is an infinite many that are equivalent to 3/5 if we were to continue our number chart and continue past the number 12. What number will make this equation true? 2/3 is how many twelfths? How many copies of 1/12? So I see on my number line, I have 2/3, but I want copies of 1/12. So therefore, I will cut my pieces into twelfths. So 4 from 0 to 1/3, 4 from 1/3 to 2/3, and 4 from 2/3 to 1. And then I can count how many copies of 1/12 it takes to arrive at 2/3. I see that there are 8 copies of 1/12 in order for me to reach 2/3. So 1, 2, 3, 4, 5, 6, 7, 8. What number will make this equation true? 4 copies of 1/12 is how many copies of 1/3? Instead, let's use an area diagram. So currently I have 4 1/12 shaded. I also see that this kind of separates naturally into thirds. The top, the middle, and the bottom layer represent thirds. And I see of the ones that are shaded, only one of the thirds is shaded. So therefore, 4 copies of 1/12 is the same as 1/3. Using the Sharing Pizza discussion board, complete the following, upload your work back into the discussion board, and respond to at least one classmate's answers and/or thoughts. The meaning of addition stays the same whether we are adding whole numbers or fractions. We can think of adding as putting numbers together to make a total. So let's use a number line to show the sum of 2 copies of 1/5 and 6 copies of 1/5 together is 8 copies of 1/5. I have my number line here and it's broken down into copies of 1/5. And we'll start with 2 copies of 1/5. So we start at 0 and I go to 2/5. Well, I need to count 6 copies of 1/5 more. So I need 1, 2, 3, 4, 5, 6 copies of 1/5 more. So altogether, we arrive at 8 copies of 1/5. Use a number line to show the sum of 4/6 and 2/6. So I have a number line which is broken down into sixths. I first need to start with 4 copies of 1/6, and I need to go 2 copies more of 1/6. So I arrive at 6/6, which is the same as 1. Let's use an area model to show the sum of 7/12, 3/12, and 9/12. So I see I have an area model which is broken into 12 pieces. So I need 7 copies of 1/12 colored in, and I need 3 copies of 1/12 colored in as well. And further, I need 9/12 copied in, but I only have 2 left, which means that I need to bring in another set. So I have 1 full unit colored in, and I needed to bring in another one so that I could finish the remaining 7 copies of 1/12 being colored in. So if I were to add all the copies of 1/12, I see that there are 19 copies of 1/12 shaded in. So there are 19 twelfths. This is also the same as 1 whole unit plus 7 copies of 1/12 or 1 and 7/12.